Last but not least, we have a guest speaker tonight, Tom from Dell. Tom will talk about how data will help you cross the finish line. So with that, Tom, the floor is yours.
Thanks. So my name's Tom. I work for Dell Technologies. Thank you all for being here. I have a few shameless marketing slides which I will use to give you context. But yeah, let's dive into it. First question you might have. How the hell does a Formula One company go to a laptop company in order to become data-driven? Good question you might have. Reason for being so is that you may know Dell from one thing most certainly, and that's our end-user devices. End-user devices are our staple. This is not a Dell, by the way, don't get it wrong. This is a piece of technology fruit. But yeah, still, most of the things we do are hardware-driven. Now, the thing is that 50% of that big number you see up there is this. It's laptops. Now, I don't need to tell you laptops are low-margin business. You don't make a lot of money on selling a laptop. So you need to sell a whole lot, and you need to make sure that your process is as optimal as possible. So when you look at Dell, you see Dell as a technology company, but actually what we do is we run one of the most complex and most efficient supply chains in the world. Because the cheaper we can produce a quality device, the more profit we get out of it. So that's a concept of marginal gains, and that will come back later, by the way. So bear that in mind, marginal gains. That's our mantra, not super important. What is super important is we try to build sustainable. There's a few reasons for that, because the Earth needs it, obviously. But again, imagine this piece of technology fruit was a Dell. A brand new Dell. It would, for example, contain a modular baseboard. Why is that good? Modular baseboards means that if we have a system with a problem on the motherboard and we need to replace a part, we don't need to rip out the whole motherboard, throw it away, put a new one in. We can just put in a piece. Again, only putting in a piece is a lot more cheaper than doing a full motherboard. So we try to build sustainable for ourselves, but also for the planet. As mentioned, we are a hardware infrastructure company. But as you can see, 87% of engineering we do is software engineering. It's about our IP. We take in silicon from all sorts of other vendors. You might know them, the Intels, the AMDs. We put some IP on there, and we deliver a new product. So even though we are a hardware company, we invest a lot in software, also, again, for that supply chain. And we don't do that alone. We don't make hardware for hardware's sakes. We do that with ISVs. We try to bundle our products in ways that it is easy to consume for you as an end user. Whether that be in a data center, whether that be for a end user device, etc. And one of those examples in the data space is, for example, we've built a purpose-built appliance for a data lakehouse, meaning that you don't need to acquire hardware, put in your own software. We can put it on the floor, it's a validated design, and it will help you get to better results faster. And that's a little bit what we try to do at Dell, and that's also one of the reasons McLaren contacted us, because high-quality labeled data is your driving leading factor. So talking about McLaren, why did they came to us? First of all, this is a true partnership. It's not like we pay McLaren money and then say we are the official barista or the official ice cream maker of a certain Formula One vendor, because you see a lot of stickers on the car. It's basically a true partnership, because what you need to realize is 10 to 12 years ago, McLaren engineering wasn't that really good. I mean, to be fair, it was a victory if they crossed the finish line without problems. So there was an engineering problem. They looked at us and they said, hey, you're quite good at that marginal gain stuff with the way you organize your supply chain. It's something we want to do as well. And the gain for you is then that we buy your hardware. So great, let's work together. And it's become a true collaboration between the two parties, where it extends beyond what we do together, but we also try, again, to be more sustainable. We try to do good. So, for example, we have a technology which is called the McLaren Substitute Teacher, which is trying to get STEM subjects to life through the concept of Formula One. So, let's talk about McLaren now. A little bit of history about Formula One, about McLaren. racing, or I would say car racing, is as old as the first programmable computer. So it started in the 1950s, but it was a mechanical sport for a very long time. So how did the first designs happen? Somebody got onto a table, he took a big piece of paper and he started designing a car. And it was for a very long time like that, up until 75, where McLaren was actually the first company to also put telemetry back into the car. So they just weren't building a car, they were also going to look at that car, how it performed, and we're going to use that data back again in order to gain better insights in that. So they were the first to do that already in the 70s. But it's only until the 1980s where we see the rise of electronics that we actually see a lot of more evolution happening in the car as well, whether it be through fuel efficiency, whether it be through drivability, etc. And in the 90s, we see that explosion of computing, not only in the car itself, but also on the side of the track. On the side of the track, we now see the people with the computers, the analysts, trying to do things and making sure that the teams perform better. So today, F1 relies on every piece of, I would say, technology that you know, whether it be edge, whether it be 5G, whether it be hybrid data centers, and they connect that around the world 10 times the speed of your regular broadband. Why is that? Trackside people are limited. If you are a Formula One team, you can only bring so many people to the side of the track. It's a limited number. And you need guys to change the tire, you need guys to change the fuel, then you need the team leads for the race itself, so there's not a lot of space left for the people who do the actual analysis. They do it in a data center, which is in the UK for McLaren. So it's real-time analytics during the race being done on a remote location and on track as well. To give you an idea, why would a Formula One company invest so heavily in IT? Again, marginal gains. How competitive is Formula One? Very competitive. So yeah, the performance difference between the fastest and the slowest Formula One car is 4%. And for the top 5, it's only 0.15% in actual car performance. That means that anything that you can do better in the performance of the car gives an immediate effect on the track. So there's two very important things. That's the car and the rider. You need the best rider in the best car. And this is also acknowledged by the riders. So you might know this guy, it's Lando Norris. He drives for McLaren, and this is a quote he had to say where he is also really, I would say, very positive about engineering and the car manufacturing. Again, last year McLaren won what's called the car manufacturer's title, basically acknowledging their success with the car itself, independent of the driver, meaning that from going 10, 12 years to barely finishing the race to having the best car on the track acknowledged by the other car manufacturers is quite an achievable feat. And they did that through a data-driven strategy. So why is data management important and why is data important? A Formula One car is not a car. It is a programmable piece of prototype which is driving on 4 wheels. Every car has about 57,000 components. They design a new car prototype every 17 seconds digitally. Now, obviously, you don't want to make those cars constantly. You do it digitally. And 90% of the race car is modified during the season. What do we mean by that? Once you build a car, you can't really touch it anymore. You can't change the engine during the season. You can't do any big changes to the car itself, but it is a constant tweaking of those 57,000 components, 75,000 components, excuse me, that are inside that car. So, in order to be able to create a prototype every 17 seconds and see if it performs faster than the last one, you need a lot of data. And to give you an idea how is that happening, this is a difference between an MCL35M and MCL35. A lot of the car changes are not only driven by performance, but also by ruling of the Formula One. So you see here The previous version, they had a square, I would say, base of the car, which is no longer allowed. It needed to be diagonal. That gives you about 10% less downforce. Downforce is basically what keeps the car on the ground and keeps it from going up. So if you have 10% less here, you need to make it up somewhere else to make sure your car does not become a plane. So these are a few of the examples. This is the model where they also changed the engine. So they went back to a Mercedes engine. That engine had a different dimension, meaning that they needed to extend the wheelbase again. Now, all of these changes you need to make before you get your car on the track in the season, while you are also competing with a totally different car during the season. So it's a hell of an engineering feat to be able to get a working piece of equipment like that on the track first race of the season. And how do they do that? They do that with telemetry, a whole lot of it. Today, one single Formula One car contains more than 300 sensors, 100,000 data points, and they use it for two things. They do it for split-second decisions during the track, and they, again, after the race, take all of that data, put it back inside their system, inside their digital twins, to again get real live data to test on the prototypes they are making digitally. So it works in both ways. They get new data from the race, they use that within their fluid dynamics, within their car prototyping to again make better cars. To give you an idea, it is 1.5 petabytes per race that they clean down again, send up, and yeah, so they don't use all of that data because then we would be a very rich company, but yeah, okay. What is it used for? Strategic making decisions, because weather conditions are not always the same. So they need to test the car not only when it's sunny, they need to test it when it's windy, they need to test it when it rains. So driving simulation in terms of weather conditions, super important. But also, not only the car manufacturers use this, also the racetracks and the Formula One itself uses kind of that data. For example, Formula One maximized their sponsorship during COVID because there was nobody trackside, so they used AI in order for sponsor placement to make sure that which places of the racetrack with limited cameras come into the best position, have the most exposure on TV, getting better sponsor contracts when there were no people attending the race during COVID, for example. So all of that data gets collected into a data center which is next to the racetrack. So the moving circus of Formula One actually also contains a data center that goes from Tokyo to Las Vegas to Francorchamps to whatever. And in first instance, that data is used to win the race. Why? Because you need to make split decisions. Because to give you an idea, a single lap in Francorchamps is between a minute and a minute 46. So if this is, for example, an analysis of tire wear. So tires, they are very, very good until they aren't. The problem with tires is that they perform until a certain moment and then the degradation becomes very, very steep. So it's not like it's a linear regression. The moment a tire is going bad, it's going bad really fast. So it is very important for them to make sure that they have that idea, like, will this tire still live another 2 minutes or not? If not, we need to do the pit stop. And you'd rather do the pit stop if the gas tank is already empty as well, so you only need to do one pit stop instead of doing two. So it's a constant decision-making process which is happening on what is the perfect time for a rider to go to pit stop, to refuel, to change his tires, etc. So, and again, predicting your pit stop accurately will make or break your race. If you need to do a second pit stop, even though they only last for 10, 15 seconds, it can already be too late. So as mentioned, racing strategy, command and control happens on a data center which is trackside, but it also has a direct connection to their main data center in UK, which then also becomes the point to which they upload all of the racing data they need for the later simulations. So it is constantly real-time and analyzed what's happening during the car. Do they see component failure? Do they see anything else? But it's not only done by the people who are race side. There's a whole team of analysts who are actually working in UK in direct connection with the people who are trackside as well. So it's a real collaboration between what we would call a hybrid setup. And all of that data gets fed into certain AI systems. We like the word AI. First of all, parts on demand. It's very, very expensive to build a race car. So it's also very expensive to maintain a race car. So what they do is they do not only build new cars, they also try on a per component basis, try to see what is the wear on a certain component within the track. Meaning that some components might only live for one race, some components might only live for 2 races. Meaning that they do a parts on demand, so they're not going to keep stock of those 70,000 components in a warehouse. They build those parts on demand and they are constantly looking at their data to know and they simulate that when will a part break? How many races can we get out of one single part before we need to change it? Also, we've talked about sustainability and then we talk about Formula One. These are usually 2 things that are not really going together. But to give you an idea, why are they doing this digitally? This is an image of a wind tunnel. A wind tunnel approximately uses 10,000 kilowatts per day. And it will cost you 10 million a year in electricity alone. And it has about an efficiency of 15%, meaning that 15% of the electricity and the money you put in is actually converted into wind. So it is a very, very costly system, which also the FIA is trying to get out. We are trying to do a wind tunnel phase out by 2030, meaning that everything which is fluid dynamics needs to happen digitally at a certain point. So this is where the digital part again comes in. They can no longer test the physical car in the wind tunnel. They need to test it digitally. So this is where the HPC digital twin part comes in. Everything that they design about the car needs to be digitally verified first. So the digital part is the single source of truth before a car ever gets made into the real life. So it's only when they are 100% certain that a prototype will perform better than the next one that they will actually build it. So it's not just fluid dynamics. If you build a new prototype of your car, you need to build it 4 times. 2 for during the race, because if you have a car breakdown, you need to get another car. 1 for training, testing purposes, and 1 car for safety purposes. So basically every prototype they build, they need to smash 1 into the wall to see if the driver is safe. So again, the more you can do digitally, the better. Also, racing strategy and simulation is completely done in a 3D way, where there's actually a simulator that will completely give the rider the look and feel of the real car. So when they are testing a new prototype, they will never go into production before the rider gives his go-ahead as well. And this is tested on the model that they think is going to be a good race car by the riders themselves. So here the riders will test the car and actually tell them like, okay, this model too much downforce, for example, this model too much oversteer, etc. So they use that rider feedback again before they actually put the rider in that physical car. It's also used for simulating the track, meaning that if a rider goes to a certain track, he's driven that track in his car already 100 times, for example, digitally, before he ever sets foot into the race. They get about 99% accuracy, meaning that the way the car responds digitally is 99% the same as it responds in real life, which is super important because if you're going at 300 kilometers an hour and the car doesn't respond the way you think it does, yeah, stuff might happen. So again, it's not really about how they do that data platform, but why they do that data platform. Again, marginal gains. This is one of the most competitive sports in the world. Everything that you do has an effect, and it costs a lot of money as well. So you need to get it right the first time. So if you are in a very high competitive market, I think it is imperative that you take on new technology in order to make sure that you stay ahead in the game in your market. And that is all I had. We're 5 minutes over time on the agenda, so sorry about that. I hope it was interesting. If there's any questions, please find me downstairs for a small drink before we leave. Thank you.